is everybody there and ready to listen?
Yay!
Yeah, everybody. So today I'm going to talk about a subject more related to operations, infrastructures, especially something related to Docker orchestration. It's a technology I started playing around about 2 months ago, so I'm still quite new into the topic. This is Kubernetes. So I have a little reminder also for myself. Being French, I always pronounce it the wrong way. They say Kubernetes or whatever. So I think proper way is Kubernetes. If I do mistakes, don't bother. I will make it. Well, so who has already heard about this technology?
Heard?
Okay. Who has heard it? Persons? Okay, great. So let's get started. So since I'm quite new in this group, I'm going to present myself. So my name is Antoine Cotten. I'm a technical operations engineer at Freeletics. If some people were at the last meetup, they probably met me already. I do mostly virtualization and automation related stuff, like server provisioning from bare metal, configuration management, and more recently Docker related stuff. So I'm going to tell you what this talk is not about first. It's not a talk about Docker. I will assume that most of you already heard about Docker and know the basics, but if you don't, it's not a problem. It's not blocking for understanding this talk at all. It's not a contributor's point of view either. I'm not a contributor into the project, but just a user. So if I do mistakes, if I do errors, and some people know more about me, please correct me. And I'm not going to compare Kubernetes with other orchestrators either. It's not the point of the presentation. There are many in the Docker ecosystem which are really good. It's just my approach to this one. So, it's a talk to introduce you to Kubernetes. Now, telling you the basics, talking about the key concepts. I'm also going to do a live demo of the key features of the technology, sharing my experience on provisioning this cluster on AWS, and it will be especially end-user oriented, not developer oriented. So, my first motivation to start working with Docker, what got me started, was probably the portability of the solution. Docker has a very high abstraction level, and working every day with developers, I know that it's quite hard to work on different platforms and have dependencies management which work correctly, even if most of the programming language nowadays have very good dependency management. You cannot control what version of the software your developers use, for example. Local testing is always a hassle because it's very unreliable, in our case at least. You need to provision platform for your developers so that they can test. They cannot test together if several people want to test on the same platform. It's always complicated. With Docker, you can have just one runtime, one Linux OS, and you can run pretty much anything. At least that's the promise of Docker. It works really well with distributed application, which is our case. It encourages you to actually have microservices over a monolithic application. So this is something that we would really like to leverage for our applications. The second motivation is that we deploy often, and we don't currently have a lot of efficiency in our deployment process. We work with OpsWorks, if some of you also know and heard about it or use. With OpsWorks, every time we want to scale up or down, we would have to decommission or provision new servers. It takes a lot of time, because first you have to provision the AMI, then Chef will take over and start configuring the server. Most of the time it fails at creating some folder, and then you have to roll back and deploy a completely new application. When it doesn't fail, it will deploy an app, but it will take a lot of time, like 14 minutes for us is the average time for deploying a full-featured service. This is actually too much. When you have a lot of people in the evening, for example, a lot of traffic, we need to scale up or down really quickly, and this is not possible right now. So we can bypass the overhead of this configuration management by using something like Docker, where everything is prepackaged, and you just have to start one process on your machine. You reduce the time from minutes to actually milliseconds. So, the reality of Docker is that it's not that easy. Oh. Yeah, I'm a big Apple lover now. I know even more why. start from the beginning? So where was I? Okay. So the reality of Docker in production is like not so easy. The promise is that you can run your application anywhere, but how do you scale your application? How do you think about the composition of your application, the scheduling? How do you make your application communicate with other containers? This is always something that you need in a real life scenario. Docker is just for running application, but it was never made for shipping them. So what you have to do is struggle with a very big ecosystem, which will let you implement like composing your applications by considering these different topics. The composition first, how do you put your different blocks together? Usually when you got an application, you always have some front end, back end, databases. All these things need to run on specific machines. This is where you need some scheduling, for example. Most of the orchestrators nowadays tell you that you can run your application anywhere and start on any node, but sometimes you need more control than this. Some application must run on the same node, for example. The networking is also something you have to consider. Can all your containers talk to each other? By default, not. You need some network overlay to enable this with Docker. And also the storage. How do you persist your data? If you have a container running a database engine, which I don't recommend, but you could do that. If it stops and starts on another host, you would lose all your data if you don't have some solution for it. So this is what Kubernetes tries to solve. Kubernetes or any other solution. If you take a look at the Docker ecosystem, it's pretty dense, and this is just like a part of the iceberg, the visible part of the iceberg. If you want to really orchestrate your containers, you would have to pick into one or several of the solutions, configure them to work together. It's like a lot of work. It's really complicated, and you have to experiment a lot if you want to come up with the right solution. So Kubernetes solves like most of these problems. It's a system for managing your containers on like across a cluster of nodes. It was developed by Google originally for their cloud platform, so GCE, but now they opened the code so you can pretty much run it anywhere. It's a pretty active project. There are around 800 commits per month. It's really active and hard to follow, I would say. If you really want to be involved, you would have to pretty much look at the commits every day and also spend some time on the RSC channel. So get ready to this. So why Kubernetes? It solves the problem I mentioned before. The orchestration, the service discovery, the load balancing are the main topics that are approached by Kubernetes. It also implements, since more recent versions, some storage drivers. So you can integrate it with Elastic Block Storage, for example, or mount IACC targets directly from Kubernetes. It could be interesting to solve the storage issue. It also has its own mini configuration management managed by secrets. So you can integrate your secrets into Kubernetes and allow your nodes or pods to read them. This is very convenient. But this is a big picture. Kubernetes is very API driven. It has a high-level RESTful API that you use to communicate and to distribute all the load around your different machines. So at the center of the picture, you got this master node. This master node, it runs a number of unique services that will then propagate the load on different machines. So what you can see here is first the API server that you connect to that deals with authentication and which has a couple of scheduler also used for, as I said, scheduling the machines on the different nodes. The nodes are also called minions. The only thing you need to run a minion are two components, the kubelet and the proxy. The kubelet is the client, I would say. It's used to communicate with the API, so write and read. It does a lot of things, especially scheduling the pods, health checking, for example, if you got a pod, so a group container which is failed, it will try to restart it, and if it fails on the same node, it will restart it on a different node, these kind of things. This is transparently managed by Kubernetes. We will do a live demonstration afterwards, but I wanted to show you the pictures, all the different services. The configuration is stored in a distributed storage called the GCD. If some of them have played around with CoreOS, they know it already. It's the core of the operating system. Yeah. So all the changes are checked in real time from the kubelet to the API. This is very important to mention, so you can track the failures immediately and take the appropriate actions. So I told you everything is API driven in Kubernetes. Means when you want to create the API either by curling it or in your browser or anything, you can have a description of every object as a JSON file. The same format you would use to create objects. So let's take a look at the node, for example. Maybe it's not important to analyze everything, but what you can see already is the number of CPU on your node, the memory that your node has, which will be used by the scheduler then to take the appropriate decision on where to start this or that service. This you can also do manually using things called labels, which are key values associated to every object. So if you want to start a database on a node which has much faster IOs, for example, you could match the labels and start it on the appropriate node. You can see the IP address, different information about the operating system. This is quite basic, but it's easy to understand. Okay, so what are the work units of Kubernetes? Mainly 3 work units: the pod, the replication controller, and the service. I'm going to describe all of them one after the other, and then we will do a live demonstration to see how to compose them into one working service and one application. So the pod is the smallest unit we can actually deploy in Kubernetes. It's a collocated group of Docker containers which would share some resource. So let's say you want a backend and a Redis server running on the same machine for some reason, because you want to share storage or network. You can collocate them into a pod, and every one of the containers inside this pod is able to communicate to each other using localhost, for example. So you would address your database using localhost port 3306 if it's a MySQL database, and don't have to bother about the network considerations. They can be created individually, but what you do usually is create them through a replication controller, which is the next work unit. First, we will take a look at the API representation of this pod. What's important to notice here is, if some of you have already experimented with Docker, you can see the image, the name, the ports that you will match on your node, also the IP address of the pod, and different information. And once again, if you want to create a pod, you would use basically exactly the same representation, except you would remove the status part, for example. So you would give the kind, the API version, describe the specs, give it to Kubernetes, and it will create everything for you. So once you get actually confidence and you understand the API, it's very fast to deploy services. The replication controller now is the one that manages the lifecycle of your pods. So as I say, usually when you create a pod, you do it through a replication controller. Why? Because simply the replication controller allows you to scale horizontally your application by starting different pods and controlling their number, ensuring all the time you have the desired number started. So if you create a replication controller with a replica value of, for example, 5, Kubernetes will always make sure that you've got 5 of your pods running in the cluster. Wherever, on which node, it doesn't matter. It takes the decision for you, or you will have to give some hints, like I said, depending on the memory, the labels. But it will enforce at least the stages of this by leveraging auto placement, auto healing, auto restarting, and the replication, of course. You can also perform rolling updates. We will make a demonstration of this, but this is something that interests me, especially for what I mentioned before, for the software deployment. So, not much changes here. The only thing you have to compare to the pod description, the only thing that changes is the number of replicas here. The rest is all the same. And also what you can notice here is the selector. When you create a replication controller, or a service, which I will describe later, you associate labels to your pods and to your replication controller, so that your replication controller can match with desired pods. You can, as I said, start pods individually, not in a replication controller. But if you want to replicate them later, you would have to match them somehow. So you use label for that. Key values, which you can define as you want. They're completely free. I defined here a name, for example. So that you can example, you could have a version, you could have a topic, you could have anything there. And the last working unit is a service. This is probably the most interesting one and what makes Kubernetes so unique. Service is actually, I wouldn't name it a service myself. I would name it more something like a load balancer, or, well, it's a very complicated unit. It provides a name first and an address to a pod. So if you want to access it from the outside, or even from the inside, and don't want to do some load balancing inside, instead of communicating directly with your pods, you would communicate with the associated service, which will then replicate the load between your different pods. It can integrate with some local DNS as well, so it means if you have a service called Redis, this can be exported to a local DNS, and all the different containers in your net cluster will be able to address the service by just the Redis name, or Redis dot whatever name dot local. So you don't have to, I don't know, query some external service, which would be impossible in Docker cluster because you always have local addresses. It acts as a basic load balancer, as I said. So when you create a service matching using labels different pods, it would do some round robin on all your containers and spread the loads, so you don't have to create yourself an external load balancer, for example. Maybe in a real life scenario, you would also need to create external load balancer, and this is supported by the service. It has some integration with, for example, the Google Cloud load balancers, and also AWS is on the roadmap, so it's not supported yet, but you will be able to soon, when you create a service, also instantly create a load balancer, and when you take down the service, also take down this load balancer in AWS. But there are some very interesting features for the integration. Right now it's like really targeted at Google Cloud Engine, to be honest, but the community is so big and the project is so active that soon, one version after the other, will have a better integration with AWS probably. Okay, so when you create a service, there are a lot of things going on. It's not only having one layer which you don't know what's going on around it. It actually starts by querying the API server. The API server has all the truths. It stores all its configuration into the etcd key value store that I told about before, and watch constantly if something is going on. So if new services are created, if services are destroyed, it will like check the endpoint all the time. Depending on what's going on here, if there is a new service to create or destroy, it will add rules into IP tables on the local machines. So when the client tries to connect to the service, it will be redirected to a random port internally, and this random port is matched to then like one of the ports. So through the service, makes everything transparent. It means you can also access any of your like nodes in the cluster using their public IP address, for example, and never know on which node you will be redirected, because in every node these rules will be created, and internally you don't have control over this random port. So you just have to work on the service level. So API representation of the service. Also what I mentioned before, what's interesting to see here, for example, for a service is the port. When you create a service, you always associate a port, which then will be mapped to your pod of containers. From here, you could, for example, map a port on the host, which will be different on the container. This is where you do it. You do the same in Docker. When you start a container using -p, for example, you would match a port on the host to a port in the container. And this is exactly what you do here. If you don't select one, it will be randomly chosen. So if you have a web application, for example, beware, always map port 80, for example. If not, a Kubernetes will run it on a random port, and it will be very hard to address. Okay, so let's start with an example now. How to scale an application, very basic application. I will use one of the applications which is actually in the GitHub and which is taken in example quite often. It's a guest book. So we have here one front end PHP based, which communicates with Redis servers. So one master and a couple of slaves. So we'll start with two front ends and one master, two Redis slaves. The aim here is to, like I say, the guest book, you will be able to write message in your application which will be written to the slave, and when you do a read request, they will be targeted at the master. It allows you to scale your application up or down, and like either on the back end or the front end, if you scale up the front end, you use the corresponding replication controller. If you want to scale the back end, we would use the slave replication controller. So in the end, the picture will look like this. We have a front end service mapping one port to the port 80. So in our case, it will be port 80, I will not map port 998. This service will be used to communicate from the outside with our front ends. So as a replication, as a load balancer. The load balance, the front end then will communicate to its Redis slaves using also one service. So you don't have to, for example, reconfigure your Nginx to communicate with like different backends. When you add some backend, you just ask your Nginx to communicate with the service address, and the load balancing will be done internally. And of course, one Redis master, which will remain just one individual machine. So in this case, we wouldn't need to create a service, but we'll still do it for best practice. Okay. So let's check the UI first, which is not really pretty at the moment. But the company, the Kismatic company behind Kubernetes, is actually working on a new version which will allow you to manage your service. It will not be read-only like right now, and it will be much more usable, but right now it's only a development version that we cannot deploy easily. So I unfortunately didn't have a demo version for you today. But this is not the point. Okay. So let's start with the front-end service. So I got this example from the GitHub. You can easily find it also yourself. If you go to the Kubernetes GitHub and go to the examples, get the guest book thing, and you will be able to start exactly the same application as I have. So we have a couple of units which are already created here. Just to show you that it corresponds to what I demonstrated before. The front-end controller is simply a description of first the containers that I want. So the example guest book is a container which is pre-made with my application, my PHP application, where I define a port. So which port I map to. It will be very important for the service later on. And how many replicas I want. You can see here that I will start my application already with two containers. So to start with, we've got a client CLI called kubectl, which you just call by kubectl create -f if it's a file. Google on GitHub, front-end controller, files, the Wi-Fi. My replication controller is started. So we can now have a little overview about of what's running in the cluster. First, I can confirm that I have two nodes here. By just typing kubectl get, so it either node, code, replication controller, or service, all the units that I described before. So I'm running a cluster with two nodes. So one API server, of course, and two nodes, one master, two slaves, in which I'm running different services. So first maybe the replication controller. RC. You can already spot my front end here, which is running with 2 replicas. So I'm sorry, the window is a bit small, it's hard to read. You can do some filtering using the labels. You can see, well, it's hard to see here also, but the selector corresponds to the labels. So if you want to shoot only, for example, replicas with one specific label, you would just type name equal front end version equals whatever, and it would list only the corresponding things. Why I opened the UI here is because you can do exactly the same for visualizing your cluster using the web interface. So if you type name equal front end here, you would just have the units related to this label. So here you can see that one of my pod or container, because it's a pod containing just one container, is running one version on each node. So Kubernetes took care of spreading them across different nodes. So if one is down, you can always have some replication. Next, let's start the corresponding service. So front-end service. And there you go. Normally, even if we don't have a backend, we should be able to connect to the host, any of the hosts, and already see our application running. Not the case.
It's an internal IP.
Yeah,
you use the internal name.
This is what
yeah,
so
exactly.
I'm going to take what we found. Yeah, because it maps all the internal IP on AWS. And the guestbook is running. If I try to type something, of course I will not have any answer if I maybe put a message in the guestbook. Nothing will happen. So we need also to have the corresponding backend. So same thing is happening here. I would create my Redis slave controller and the corresponding service. Let's check it right here. Redis slave. And we also have 2 slaves running on 2 different nodes. So I should be able to write a message now. And there we go. But since the read are done on the master, we don't have a message if we refresh the page. So what we simply do is create the Redis master controller. And the corresponding service. And now we can submit messages. Message 2. And actually have them persistent. So all the scaling was done using this JSON file that you described and passed to your API, and Kubernetes will scale them for you. One of the use cases now I would like to show you is that if you want to resize your application, for example, I need more backend, I have too much load, you would simply get your list of replication controller. So I want to scale my state, for example. Type kubectl, resize, RC, give the name of my RC, and be a bit crazy here, for example, I want 20 backends, and it's immediately going to resize them for me and update the cluster. This is really fast. I mean, performance is probably the most interesting feature of Kubernetes, and also ease of use. And you could do that with any of the services that you're running inside the cluster. The next feature I wanted to show you was the rolling update. So I'm going to scale back to 2. By default, every time you do a rolling update, it's going to take 1 minute to refresh or to replace one of the pods. So for that you got a trigger, which I never remember. Maybe somebody knows. For the rolling updates. It should be full interval. 3 seconds should be fine. And that's when it's on the backend. So now I'm going to replace my, let's say I have a new version of my ready slave. I will simply update the unit. So I did it already here. What I changed here is just change the name, add a new label here called v2, and also in the template. So I can match with my selector the corresponding template associated to my pod. So, rolling updates. I will change the timeout so it doesn't take too long. And I start doing the rolling update of my replicas. So first we are going to replace the version 1 of the first ready slave, and after some time is going to take down the second one and start the ready version 2. So it was obviously not the right trigger. The full interval is not the one I was looking for. But you get the idea. I mean, if you want to do an update of all your application, which is running over 30 containers, you just have to change the tags. For example, in your Docker container, input a new version in the labels, and run a rolling release. And it's going to take care of replacing them one after the other, so you don't have a downtime. You don't have to take down the whole application to bring up the new containers. You just run this rolling release, and you're done. So that's it for the demonstration. Do I still have time?
Yeah, sure.
Yeah.
How much longer?
Not much. 5 minutes. I wanted to talk about the provisioning on AWS. Basically, you got two options right now. Kubernetes comes with a provisioning script called kube-up. So the only thing you have to do when you run this is exporting a couple of environment variables to define how many nodes you want in your cluster, on which cloud provider you're running, what kind of instance you want to run. The only problem with that is that you don't have much control. It's going to create the instance for you, it's going to run salt, configure the machines, provision some random secrets, and configure your workstation. But after that, basically you would have to do the modification by hand if you need to change like configuration in your kubelets or any other components of the Kubernetes cluster. So it's okay if you like Ubuntu. It's going to like start Ubuntu instances by default. It's not my favorite operating system for running Docker. For example, if I want to change anything, I would have to go into the salt configurations and change the recipes myself. Well, this is okay for testing, but not for real life scenarios, and not for starting a container like I want, a cluster like I want. I would prefer to use Cloudformation for this. Cloudformation is just a big JSON that you would give into AWS. It would create your whole infrastructure, configure your Kubernetes cluster as you define. The problem is that for people who know about it already, it's just a big JSON that you give to Cloudformation. So it means you would have to put all the secrets in clear text inside the configuration. You end up with like several pages of code for just configuring your services, which would be much more efficient to use a configuration management tool. The problem is that CoreOS, for example, the OS I use, which is meant especially for running Docker, has a very good integration with Cloudinit, so which is used by Cloudformation, but it doesn't give you much freedom. You cannot provision secrets without putting them in clear text inside it, for example. You would need some kind of configuration management, which is not really supported by CoreOS because it's a minimalist system. For example, Chef is not supported on CoreOS, neither is Puppet. So as I say, it's limited and it's unsecure. There are some projects which are emerging, like for example, you can still use Ansible. Ansible is only working over SSH, so it's easy to run it from a local station. Once you provision with CloudFormation, run Ansible once and configure it. like easily, but it still means some manual steps. There is also a project which has been started recently to run Puppet on CoreOS. So I encourage you to take a look. I haven't tried myself, but I'm definitely looking into it. And yeah, if you want a correct approach, I think configuration management is necessary. So yeah, this is like visualization of what you get when you run my Cloudformation template. You can select a couple of parameters, but it's very limited. So thank you very much for listening. I hope you were interested in it. And as you said, there are some rough edges in Kubernetes, but it's still very powerful. Just need to keep an eye on the project all the time to see what's going on, because from one version to the other, things will break. Like I just noticed this morning, for example, that my monitoring was not working anymore, my Grafana, which is supposed to be like an integrated add-on into Kubernetes, but since the last version, it just shows you the monitoring of what is running on the same server as Grafana is running, or keeps collecting service. So you cannot run it in production right now, but still, as you saw, the features are very powerful and it's very promising. So it's going to be a major actor in Docker orchestration in the future. Do you have any questions?
Did you already have time, or maybe the effort to look into the Elastic Container Service?
No, not really. That's on my roadmap also, but I haven't.
Okay.
But it's not running Kubernetes.
No, it isn't. But actually, the whole Docker thing totally integrated into AWS.
They got a lot of inspiration.
Yeah.
For the rolling update, can you limit the number of, let's say, Docker images that it will replace? Or
What do you mean?
yeah, let's say I only want to deploy the new application or the new version of something to the 10% of my images. Or
For that, you would usually need to create a different replication controller, like something smaller. For example, you reduce your. Imagine you got 10 containers running. You reduce the number to 8, and you start exactly the same replication controller, but on 2 containers. And with one label changing, for example, you call it dev or testing. And then you would do a rolling release on just these 2 containers. But there is no feature right now. I already had the question actually, and internally in the company. And there is no like easy mechanism for it. You can do manually, as I explained, but that's the only option you get so far.
Can you connect the same service to the 2 controllers then?
Yes, with matching, as long as some of the labels are matching,
Okay.
it will like grab everything corresponding to these labels. So you just create replication controller, but the service doesn't change.
So you add a label for kind of testing environment, stuff like that,
Exactly.
and do the whole Redis master or the Redis slave the same.
If you got a Redis, you create one label called like typically app Redis, and one another called version dev or prod.
Okay.
And you do your matching on just the name, for example, so you combine everything.
Noch jemand Fragen?